in philosophy, but basically what I want to do is to evacuate this stuff here. Okay. So I think it's more glorious to go in this direction. A few nota benes. There are some complicated models, but it's still a model, or Hamiltonians, like, for example, this kinetic facilitated easing model. And Robert Jack will give a talk on this, or lectures. And so these models, they have some parameter or degrees of freedoms, different type of models, and they allow you to rationalize different types, let's say, of class-forming system. And so the people who work on this got a little bit, I think, too bold and say, that's the truth. And it's wrong. It's not the truth. This is still a model. And it's not even a theory. It's a model. And so don't get fooled by this, that even famous people claim things. It's not necessarily true. And the last thing is that if you have been around in this business, then you see theories come and go of various qualities. Some of them are really, well, not wrong, but it's really a triviality. Others are extremely complicated, unsophisticated, done by very intelligent people. So, I mean, we've seen that class physics spans many orders of magnitude in time, but I think there are also many more orders of magnitude in the quality of theories. And so don't get lost in these things. So I'm not able or willing to talk about all the theories. It's impossible. But I want to take certain things that I consider as useful. And one theory or approach is to give a phenomenological description of the structure. So that's what I want to start with. And this concept is what is called the continuous random network. This is a very old concept, 70 years old, I think. So I forgot, it's Tachar-Yazan who proposed this for the first time. And the physical idea is very simple. For covalently bonded atoms, like silica, for example, silicon and oxygen, you have a very well-defined coordination number. That is, the silicon, a priori, it wants to have 4 neighbors. The oxygen wants to have 2 neighbors. A carbon atom wants to have 4 neighbors, etc. And so once you take this very simple chemical rule into account, then you can start to construct models, but just by obeying the chemical rules, basic chemical rules. But you allow that it's not a crystal, but that you put in some randomness. And so you can come up with a rule, and I give here a rule, just an example, how to build a 2-dimensional random network. So, for example, you can say, well, all atoms need a coordination number of 3. The distance between nearest neighbors is fixed, okay? And I don't want to have loose ends. So every atom really should have 3. Not more than 3, but also not less than 3. And then if you do this, stick and balls or on the computer these days, then you get a structure like this, which is some sort of a cartoon of a structural gas, okay? And you can generalize this idea by looking, let's say, at a 2-component system where you have locally slightly different rules. So you have atoms, the black ones, that are 3-fold coordinated, and the white ones are 2-fold coordinated. And so if you would embed something like this in 3 dimensions, you would get a structure which does not look totally crazy, okay? And so this is this concept of this continuous random network. Now, surprisingly, this approach works quite well. So this is old data, 30 years or plus, where this, you cannot read it, this is amorphous germanium, okay? And so this is just a 1-component system, but which, if you can generate it in an amorphous form. And here, this is the radial distribution function as a function of the distance. And the experiment are the dashed line here. So here it's covering. Here you see a small difference, and here as well. And then the dashed line is the continuous random network, and the experiments is the full line. And you see that the location of the peaks and more or less also the height of the peak is surprisingly good. And if you take into account on the naivety of this model, it's just chemistry. Stick together and then don't care too much about angles, etc. You already understand quite a bit of the structure. So, surprise.
So, two related questions. One is, you didn't say anything about bond angles. And the second is, has there been any sort of optimization of what you're comparing to?
I don't know. I mean, the first one, I think there was no, well, I guess there must be a bond angle. I don't know, but I think there must be a constraint that the bond angle has to be in a certain range. And I don't think at that time they did any optimization. I think basically you just put it together and you get what you get. Now, so this is a one-component system. This is silica. And this is a very famous work by Bell and Dean, almost 40 years ago. And so they did this. It was really ball and stick model. I mean, balls and stick, they put it together. And they had a model of a few hundred atoms. And then they measured it. And they got out this radial distribution function. And if you measure it, then you get something like this. And okay, you see that there are slight differences, but in an approximate way, more or less the location of the peak and the relative height of the peak, for example, that this here is smaller than this, you indeed find it. And if you imagine how primitive this model is, the success is not too bad. And this is, these days, nobody's really doing this anymore, but as a concept, it's still quite nice. No, this is zero temperature if you want. Okay, yes?
Just a comment. They did these models, right? I think they took a Gaussian distribution of bond angles around some peaks.
Yes.
And they found that within a few, up to 10%, you would completely destroy Maury Jordan. The second point is they did a time-binding approximation with electron hopping on it and got this, at that time, very surprising. You got sharp band gaps.
Okay.
So that implies that the sharpness of the band gap is largely determined by the short-range coordination plus the continuity.
Okay. Okay. Thank you very much for this comment. Okay. Very nice. Okay. Other questions? Okay. So that's the only thing that I want to tell about this structural model. Another very important model or description of the structure, which is still very, 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 very much en vogue these days, is random close packing. So one motivation that you can use for this is that atoms, the first approximations, can be considered as hard spheres. This is not going to work for silicon, but for many metals, this is an approximation which is surprisingly good. And Kelton and Poole will tell you more about metals and nucleations, and many of these systems basically are just hard spheres. So what is the idea? So if you are in 2 dimension, so the sphere become disks. If you want to tight pack disks, so what you get immediately is a hexagonal lattice. In dimension 3, the motive that is best packed locally is the tetrahedron. So you have 4 particles, but with tetrahedron you cannot fill the space uniformly. And so what you do is to make a local compromise. You cheat a little bit. You take a few of these tetrahedra together and you form an icosahedron, which is a very good local packing. But again, with icosahedra you cannot fill the space uniformly. And so if you take the structure and you try to pack them as efficiently as possible, you get a random structure. So it's not that is to say a glass. And I suppose that David Welch in his talk will talk more about this sort of structure that you can get. Now, since you put together these particles, I mean, as tight as possible, there is always a little bit of ambiguity. Should you put the particle here and the next one here, or should it do vice versa? The end result makes that the final structure from a microscopic point of view is not unique, that is the location of the particle is not unique, but, and this is not surprising, what is more surprising is that even the average density of the structure that you get is not, or depends on your algorithm that you're using. It changes by a few percent, okay? And so there are people still working these days hard in order to understand what is really going on. In order to give you an idea, random closed packing, so of Hart spheres, you get a packing fraction or density of particles which is around 0.64. And compare this if you build a crystal, that is to say you build up the balls in a regular lattice, that is to say HCP or FCC structure, there you come up to a density of 0.74. That is to say you're losing about 18%. But this here is a mechanical stable structure, okay? So it is dense, but it's disordered. Yes?
So you say that there's this algorithm for this, but don't the packings become more ordered if you're away from this?
You see that that's already one, it's a very good and fine point. Now, so we are talking about random close packing, but if you order a little bit, because then you know that you can get denser, how much local order can you allow, cheat, get better packing, but it's still random. And that's exactly where the issue starts. And many of the things of this algorithm are done on the computer. And so you have some algorithm, and you get a very high dense packing, and then you say, well, but is everything really random? And then you go to look for it, and if you find a small microcrystalline, you say, well, that's not important. I still have my high density. And that's exactly where the fighting starts.
So there are no good order parameters?
Well, look, if your order parameter of crystallinity is 10 to the minus 4, are you going to complain? Some people do. It's not clear. But that's exactly the heart of the issue. Okay. Now, how well does this? It's a very simple model. Again, these are old results by Cargill. This is a metalloid glass former. So this is the G of R, the nice smooth line. So you have here the first peak. You see, this is a nice example why, at that time at least, they were not able, from the static structure factor, to calculate the G of R, because this here is all junk. Huh? You remember what I said the last time. So, but here, the things look much smoother. And so you correspond the smooth line here with the random close packing, and you see that all these features, qualitatively, they're quite well reproduced. This is the same thing, but on a larger scale. And so you see it goes out to a relatively large order, and it seems to work quite well. And what you also see here is a feature that is what they call a split nearest neighbor peak, second nearest neighbor peak, sorry. And it's nothing magic. So if the red particle is sitting here at the origin, so this first peak here are the pink particles, so that's the first nearest neighbor shell. And then the second nearest neighbor shell, basically you have, grossly speaking, two configurations. You have the red-green one, which is a distance which is slightly smaller than red-blue. And this gives, but more or less there are both of them in the second nearest neighbor shell. That's why it's splitted. Okay, so there's no magic. Some people made a lot of fuss. Well, glassiness has something to do with splitting of second nearest peak. Nothing. It's just packing, local packing arrangement. Okay.
No, I guess, I mean, for me, when I first sort of looked at this closely, it's actually surprising from a certain perspective that we do have the second neighbor at twice the distance of the first neighbor, right? So the fact that you have the split second peak does tell you that the packing structures are changed. So to that extent, it is associated with what might eventually lead to jamming or the transfer.
Fine. I'm just complaining that, I don't know, 20 years ago, people said that the onset of the splitting has something to do with glassiness, and that, I think, is not true.
But this also says that there is some intermediate range order, and this
True. And a liquid is not disordered locally; it is ordered. And here and this is a 2D cartoon. 3D, you have phase space argument in here, so it's not quite appropriate what I'm saying, but the physics is more or less there. But there is a local structure in the order. That's why you see all these oscillations here. There was a question over there. Yes.
Is this a plot of G of R?
No. No. You can't see it. It's times 4 pi r. That's why, and basically this is one of the trick in order to increase or make that the oscillations here decay a little bit slower. Okay, so you cannot read it, but good point. Okay, bad scan. Okay, so now so run close packing. This was is a good model for the structure, as you see. Now let's talk a little bit on dynamics and a phenomenological, very simple phenomenological model. Old models, 40 years ago more, proposed by Adam and Gibbs. So the idea is the following. So if you have your system, your sample with the atoms in it, the idea was in order to relax, a single atom will not be able to do so because there is no space, it's caged. But one possibility is that a few atoms come together, put together, and say everybody gives a little bit of space, and then together we can do something. And this here is a cartoon on what is going to happen. I mean, first you have the configuration like this, and instead that, I mean, the red and the green atom, they will never be able to exchange places. It's way too hard. They would have to push away too many atoms. But if these three atoms would do something like this, then they will be able to do it. It's a bit much more easy to do it. And so here you have some sort of cooperative motion, and that gave rise to the name of cooperatively rearranging region. That is to say, this is a region which goes together and flips. And for the following, so I will go now through a little bit of math. The idea is that these CRRs are independent of each other, so something's going on here, something here, independent events, and that the number of particles within each of these regions is sufficiently large that they can do statistical mechanics. Okay? Now what you're doing is you focus on one of these events and of these regions, and you write down isothermal isobaric partition function, which is here the exponential of minus beta h, with h the enthalpy, and the W here is the number of states that you find with energy E at this certain volume V, if the pressure is given, and you integrate or sum over all the energies and all the volumes that are disposable at this pressure here. And so this is just, you are doing statistical mechanics on this region here. Now, here you have done equilibrium statistical mechanics, but you are interested in the dynamics, and therefore you care only about the regions that actually can do something, that they can rearrange. And this will be a subfraction of the regions, of all the regions. And therefore, instead of looking at the partition function delta, I'm looking at the partition function delta prime that looks only at those regions that can actually rearrange. We will see the details a little bit later. And therefore, the fraction of the system that can undergo such a relaxation event is just delta prime over delta. And if you plug in the delta and delta prime, and you use the Gibbs free energy as definition, then you get out this expression here, and you can express this ratio here as an exponential of minus beta z, delta mu. Z is the number of particles in your region, which is considered as fixed for the moment. And delta mu, you should just see this equation here as a definition. This equation is the definition of delta mu. That is to say, it's the chemical potential per particle. Okay? Now, let's call W the probability that the system actually makes such a jump. And so, since the more entities, systems that can make a jump, the more likely is that such a jump will occur, you will say that this probability to jump is indeed proportional to the concentration of the system that can make a jump. That is to say that the probability to jump is indeed proportional to this factor here. Okay? So that's this equation here. Now, this was one system for a given Z. Now, I have a collection of systems that have different number of particles, okay? So the number of particles is k. K is 1, 2, 3, 4, I do not know up to where. And I have n of k and t number of systems that have exactly k particles, okay? And so the average probability that any particle makes such a jump is given by this expression here. So it's the number of patches, that cooperative rearranging region that I have, times the number of particles in each of these regions. So that's the total number of particles that are in a region of size Z, times the probability that such a region really flips. Okay? And here the sum starts at not at 1, but at the Z star, which will become later on a fit parameter if you want, which corresponds to the smallest cluster that actually can do something. In extreme case, Z is 2, because a cluster with one particle doesn't make sense to say it's jumping. So Z star is certainly larger than 1, but what it is later on we will see. And so you plug in the expression that we had here. In this equation here, you fiddle around a little bit and you get this expression here. So you have a prefactor, which depends on this Z star, and then you have times something. But this times something, if the beta mu, delta mu is much larger than 1, that is to say, if the temperature is very small, then you see that all these factors here become very, very small. That is to say, you can stick with the first term. And the first term is just 1. That is to say, you can throw away this sum or replace it by 1, and you end up with this. All the stuff that you don't like, you put it in a constant A prime, and you end up with this. So end result is the probability that the particle flips is proportional to this quantity here, where Z star is the minimum number of particles that can flip. Okay.
Why is the actual way that the flip takes place is not apparent in this expression?
Because you don't know, and you are just imposing, saying something is happening, I do not know how. It's certainly a justified criticism of the theory. But you are perfectly right, and I can't give you an answer because there isn't. It's just to say, let's assume that something happens, but I don't tell you what happens. Yes?
Just to add, I guess other than sort of not saying something specific, there's also a problem with the specific statement that is implicit, which is that the free energy barrier is proportional to the size of this.
True. Plenty of problems, but it works. Okay. Now, we try to understand what is the value of Z star. That is to say, the minimum size of a cooperative rearranging region that is able to do something. And so we have seen yesterday that at low temperature, you can decompose the dynamics in fast degrees of freedom and slow degrees of freedom. That is to say, you have vibrational motion and relaxation. And therefore, the partition function can also, so this is the idea of Goldstein, so you have this minimum around which the system vibrates. And therefore, the partition function, you can factorize it into two factors in the statistical mechanics that comes from the vibration and the statistical mechanics that comes from these various minimas. Okay? And therefore, also the total entropy of the system can be written as a sum of the vibrational entropy and the configurational entropy, vibration, is just the harmonic oscillators, and the configurational entropy is that this takes into account how many minimums do you have at a given temperature. Okay. Now, the number of CRRs in a system with n particle is given by this expression here, n equal a number of particles divided by z star. So here you're making the approximate, or I have the idea that everybody participates in one of these patches, okay? And so the number of patches that you have is just the number of particles divided by the number of particles within a patch. And therefore the configuration entropy for one of these patches is just given by this expression here. And therefore if you take this first equation here, you get out this. And you plug in this here, then you get that Z star is given by number of particles divided multiplied by the configuration entropy of one patch divided by the total entropy of the system, configuration entropy of the system. And now, since we have this relation here, we can plug in the Z star here, and you get out this. And so now you have a connection between the dynamics, that is, say, the probability that something happens, and the thermodynamics, which is given by the configurational entropy. Because what you do is, well, I do not want, because I'm not able to calculate this configuration entropy within a patch. I do not know what this delta mu is, but let's assume it's a constant, a weakly dependent function. And so you plug this in, and the beta gives you the 1 over t. The configuration entropy of the system is the S-conf. And so you see that the flipping probability is related to this. And now, last step is by Richard and Angel. This is what you have already seen, relaxation time as a function of Tg over T, many decades. And we are going to look at this system here, 3BRP, which I do not know what it is, but the guide. Thank you. Okay. So for this system here, you have the dynamics. You do the specific heat measurements. From this, you get the configurational entropy, and you plot these two quantities that have a priori nothing to do with each other, totally different experiments. And so here the relaxation data is the same as here. And this here is C times T, the inverse. So if this here is true, it should be a straight line. Up to you to judge whether it's a straight line.
How is it that it works down to picoseconds? I mean, it's an activated, I mean, the picoseconds, you don't expect activation.
Come on, from Rome you should believe in the miracles, no? I do not know, there is no good argument for this. I agree. The success of the theory is that for many, many years, it was just work and people did not really know why. Now, with the random first order theory, there are some hints why perhaps it works. I'm not hints, okay? But it's surprisingly good. And this is not the nicest data. You find many data where it is as good. There are also data where it's not as good. But something is there. We have not cheated here, and so we have to understand this, okay? Okay, so seems to be okay. So that's no, it's not the end of the story yet, because you can get out even a little bit more from Adam Gibbs. So experimentally, not for all systems, but for quite a few systems, one finds that the excess specific heat capacity is given by a hyperbolic law. That is to say, it's a constant divided by temperature. This was also data by Alba Simonesco, Angel, and others that showed that this here for quite a few systems is a fair approximation. You plug this into your entropy expression. You can calculate the specific excess entropy, which is given in this. You plug this into Adam-Gibbs relation, and you get out this. And this is Vogel-Fulcher law. So again, something which seems to work quite well, Vogel-Fulcher law, you can reproduce with this theory. And therefore, this Adam-Gibbs relation, as simple-minded as it seems, and it seems to have some of the truths of real glass forming liquids. Now, the critiques are plenty. First of all, we do not really understand what the CRRs are microscopically. Are they really independent? Is it reasonable that you have only one kind of CRRs? Why does it work up to high temperature where the whole thing should not really work? This is not really clear. But you have seen it, your own judgment, and you will hear many other people, perhaps not at this school, that talk about Adam Gibbs, it's marvelous, etc. That's basically what it is. Okay? Questions on this? Yes?
How should one think of these CRRs? So is it okay that if you have an ordinary phonon, it's vibration harmonic oscillation, you said, and here you basically have some kind of local mode which is rotational somehow, and therefore involves anisotropy because you have to describe the transverse direction. So, I mean, is this the right way of thinking about it? It's a kind of rotational distribution of rotation in local mode. May or may not become.
Yes, but I mean, yes, you're right, but now we need much more detail in order to understand what is really going on. Experimentally, it's of course very hard to get this, except for colloidal system. But even if you are looking at computer simulation, it's not clear at all that something like this is really happening. But perhaps we are blind that you are not looking at the right objects. But if you are just doing a simple-minded computer simulation of a glass-forming system and you look at the stuff, it does not look like this. Exactly. No.
And you look for correlations of 2 or 3 parts. Do you see anything?
Not really. It's hard because perhaps that it's there, but it's hidden by many phonon motions, etc. It's in the details where we do not know. From a phenomenological point of view, this is a very appealing picture. But then if you want to compare with simulation or real experiments, but I mean,
Is this local arrangements reversible or irreversible?
it's
Reversible or irreversible?
it's equilibrium. So a priori, yes, it's.
If it is reversible, then they won't contribute in relaxation, right?
No. I mean, it has to be reversible. So that since you are in equilibrium, if you cannot go back, you're dead. But it's very unlikely that you will go back, and that's why you have relaxation.
That's it. So you rotate it, and then you have some rearrangement in the environment, rotate back. Whether you will go back to the same state or not. If you go back to the same state,
Well, but look, this is let's say a Newtonian dynamics, and therefore a priori everything is reversible. But you have the second law, and therefore you never go back. But a priori you are allowed to go back. Yes.
I think it's important to recognize the macroscopic reversibility and microscopic reversibility. In other words, that if something happens, this may not go back exactly where that at the same place. But simply something reversible, just like the reverse, is happening somewhere else. So as an answer, one can maintain this reversibility. And also, that if you look at this simulation carefully, you don't necessarily see rotations all the time. You see them, but I mean, many things are better explained in terms of bond exchange. Some bonds are cut, and then local part will become loose, so other bonds are formed. So one bond is cut, other bond are formed in the immediate neighborhood, and that's the action. And in a sense, it is localized, and it is that happening every time. For instance, atoms would vibrate hundreds of times, and this bond cutting happens only once in 100 times. So in that sense, the Adams gives the localized description of small sort of happening, controlling everything. I think it's correct. So in a macroscopic way, we should look at this as an ensemble rather than microscopic instance.
Okay. Other questions? New theory. free volume theory. Now, this is something which is very old and has been worked on for quite some time. It was proposed first by Cohen Turnbull, and then later Turnbull and Kress took it up with a more complicated version that I'm not going to talk about. The idea is the following. Look, this is a hard sphere system. And so, each black circle is a hard disk, if you want. And so each black circle has around it a zone into which no other circle can penetrate because the other ones have a hard core as well. So here you see it basically. So no particle can enter this zone because the other particles have a radius as well. Now, if you are dense, then this particle, the A particle here that I do not show in black because it should be transparent, can move only in this white area here because that's the only zone which is not forbidden by the other particles. The B particle is more lucky. It has a zone, white zone, that it's large, and therefore it can change from here, which one neighborhood, to here with the other neighborhood. So the B can diffuse locally, whereas the A is stuck. And so what you introduce is what they call the so-called free volume, which is the volume which is accessible to the particle. That is to say, the white volume here. Okay, so it's the sum over all the white volumes divided by the number of particles in order to get an intensive quantity. So that's your V, the VF, excuse me. Now, what you are doing is to say, you're making a mean field approximation. That is to say, you are not looking whether or not these white patches here are correlated geometrically. You say every guy has the same amount of free volume accessible. And now what you can do is you make a very simple calculation. It's really not difficult. And then you find that the probability to find a free volume of a certain size is given by this expression here. So the probability to have a free volume of size V prime is given by prefactor time exponential minus prefactor V prime, okay? With Vf here in the denominator. And the gamma here is just a geometric factor, which is related to the shape of the spheres and stuff like this. Now, if you have a diffusing particle, so forget for the moment what we have here. If you have a diffusing particle, but it's not, the particle is making steps of different sizes. And the probability to have a step size A is given by pi of A, okay? And therefore, one can show exactly that the diffusion constant of this particle here is given by this integral over the distribution times the step size. And now, if you say that, well, here I have free volume, and as soon as the free volume has a certain range, I can go, I'm diffusing, you plug this distribution here into this expression, then you get out that the diffusion constant is related to the exponential of minus C over Vf. Now, so you see that if Vf goes to 0, so the amount of free volume goes to 0, the diffusion constant goes to 0, and therefore you are getting stuck. And so this is all good for hard spheres, but if you want to have a thermal system, you say that this free volume is related to temperature minus a certain fudge temperature T naught, at which you want that something happens, and the alpha is just the thermal expansion coefficient. So volume is related to temperature by the thermal expansion coefficient, and you say that at the temperature T naught, something happens. So if you plug in this Vf in this expression here, you get again the Vogel-Fulcher law. Now, again, so we saw yesterday Vogel-Fulcher law seems to work quite well. So this very simple concept is able to reproduce these dynamical features, also certain other dynamical features, details you ask Shrikant, who has worked on this. You did, no? But this is still one of the approaches that people use, sometimes very simple approaches that try to rationalize their diffusion data because they're arguing, well, if I have balls with spheres with different sizes, what is the free volume of this, and then they come up with this sort of equation. And the rationalizing this data with quite some success, one can say. Okay, so that's free volume. It's very simple-minded. Okay, landscapes. Here I'm not going to talk much about, because there will be other talks by other people. The idea here is basically, has been invoked by Goldstein 40 years ago, is that at low temperatures, not for a glass-forming liquid, forget low temperature. For a glass-forming system, the free energy landscape as a function of configuration space is very rugged. So if you are at high temperature, you are populating states that are up in the landscape, that what Austin was talking about yesterday. If you decrease temperature, the system will populate states that are down here, and these barriers between adjacent states start to increase with decreasing temperature, depending on your system. For fragile system, that's the case. And therefore, at low temperatures, you are moving in this very rugged landscape. So please note, this is a one-dimensional cartoon of what is happening. And this here is 10 to the 23-dimensional space. You don't have to think that in order to go from here to here, you have to overgo this. Usually, you have to walk around very complicated ways, etc. So this is a very bad cartoon of the reality. But I cannot do better, and I think other people neither. So that you have this very rugged landscape can indeed be shown within mean field spin glasses. And as Gupta-Mezara will talk about this in more details. Please also note these barriers are really in the free energy and not just the potential energy, because it applies as well for hard sphere systems. Okay. Now the question that people care about in this business, and the talk of Shastri and Wales will give you more details on this, is what are the typical models that you can use to describe the glassy relaxation? How many minimum do you have at a certain energy? Is there a hierarchy? What is the barrier height distribution? All these sort of things. So you can try to make a microscopic model and determine these properties, or you can say, my model is that I impose a landscape model, and the random energy model by Derrida is something like this. There's the trap model of Bouchot for the aging, which is another version of this landscape model. And so basically it's nothing else than you, as these models, that you assume some sort of a topology, energy, barrier distribution, and you discuss the property once you have imposed on how your system moves in this complicated landscape. Okay? So that's the landscapes. Questions? But there will be much more by Sri and David on this. Okay. Next, rigidity percolation. In principle, Elliot should talk about it, but it's not clear that he's coming. So this started out with Phillips quite some times ago. Then Thorpe and Boulchan and others have taken up. So people are still working on this concept. Quite interesting. So the idea is the following. So if you take an oxide glass where you have strong covalent bonds, so you have this open network structure. So you imagine that the atoms are joints and the bonds are just rigid beams. And so you can ask the question, if I have a certain number of beams per joint, is the structure rigid or not? Imagine, for example, if you have two particles, one bond, this gives a rigid structure. You have three particles and two bonds. This is not a rigid structure because you can do this. Okay? If you put in here a third bond, you have a triangle, it's rigid again. And so it's a simple counting argument on how many degrees of freedom you have and how many constraints you have. And one can show that if you have many particles, that if the number of constraints equals the number of degrees of freedom, that the structure is rigid. Okay? If you have only few particles, you have here corrections that are related with the dimensionality and that. But we are interested in many particles, and that's basically the result. Now imagine that you have a glass-forming system, that you have n particles that have different coordination number, that is to say they have different number of bonds. That's where the chemistry comes in. So if you look, for example, germanium sulfur iodide, So the germanium has 4 bonds, sulfur has 2, and iodine has only 1. And then if you use this argument, then you use a mean field approach again. You say, well, on average, I have that many bonds, and etc. Then the number of floppy modes, that is to say, of motions that you can do for free, so that you are not violating any constraints, can be shown that it's given by this expression here. So this is the number of floppy modes per particle of the system. It's given by 6 minus blah, 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 where R is the mean coordination number. So this is given by this here, okay? And so since you want to have a class, that is to say something that is rigid, the number of floppy modes has to be 0, okay? Only then it's rigid. So that's the triangle with 3 bonds. And so if you set this equal to 0, you see you have a correlation between the mean coordination number and, in this case, the number of atoms that have only 1 bond, which is given by this here. And so if you have this relation here, that the mean coordination number is given by this expression, you should easily form a class. This is in here it's in 3 dimensions. And indeed, this is really for this case here. For example, you say, I have a different composition. I do not have an atom that has only 1 bond. These prefactors here will change, or you will have then N2, etc. But you can easily generalize this approach to arbitrary number of particles of bonds. Okay. And so does this really work? And yes, it does. So here, this is a phase diagram of this ternary system here. Different compositions depending at which point you are. And so the zone 1 here, that's the region where you have good glass forming ability. Okay? That is to say, if you cool the system slowly, it really will form a glass. And the line here, yes?
Always puzzled me, you had this last line here.
That one?
Reach the conclusion, or how they reach the conclusion that the balancing of the degrees of freedom with the constraints certainly does say something about the amorphous state, but how can you say something about glasses forming easily without making any reference to the crystal? Because it doesn't discuss the nucleation problem at all. Somehow or other, there's a missing connection, which is just not mentioned.
But yes, but you see, for the crystal, I mean, this here does not apply because this is really a mean field argument, and within the crystal, this would badly fail.
I think that's a problem because of the lack of reference to the crystal here. I think Ken would probably agree.
He nods. Okay. Now, this expression here is the black line here. Okay? And so, yes?
No, I think basically, this is an argument that's developed where you have 2 very different energy scales. One is the covalent bonds that you have. And presumably the assumption is that when you make these things, the bonds form very rapidly. And even if you have a crystal when the covalent bond rigidity is not playing a role, then you have sort of a different energy fraction, energy scale of sort of non-bonding interactions. So very different. So that they're not treating the problem thermally for good reason, because whenever you have these bonds, the energy is much different. This is an athermal treatment, but they apply it equally well to ionic cases that you find them applying it to window glass and things where the covalent bonds are obvious. Anyway, it was very interesting, and it predicts some things, but why it predicts them is a little bit unclear.
It's one of these theories, again, that seem to work. I mean, there is a prediction, and I picked one example, but they looked at very different systems. Those that they published, they all seem to work. Perhaps they have a pile in the drawer that do not work. I do not know. But the point is, this is a very simple approach. I do not defend this. So you're right to ask questions. It's another theory, mean field, has some success. You will find it in the literature. If you stay in this field, you will bump into it from time to time. I just want you to understand that, okay, there is not too much into it. It's just mechanics. Whether or not you believe it, that's up to you. And you should be critical. I do not really believe in it, but
transformation is not the only consequence. For instance, the properties do change.
yes. Yes. I mean, they are able to predict how the TG, for example, changes as a function of composition. I mean, it's not totally hogwash. There is some merit into this. The miracle is just, why does it work as well as it does? And so what is the important thing? Yes?
I think a few years ago there was some development, Mike and others did in this, that in addition to the rigid phase and the floppy phase, there's kind of intermediate mixed phase where there are rigid regions.
Yes. Yes.
Could you comment on that? I mean, that's more heterogeneous and glassy.
And yes, they say that there is this soft region in there. I don't believe too much, and I don't understand too much, and rather not.
The other question I had was these floppy regions. Can they be connected to this cooperatively rearranging region?
Look, this. Yes. I think no, because this is really class physics. However, what people do, again with some success, is to correlate this with boson peak, because you have then these floppy modes. And so this is then inside the glass. Again, I'm not sure I want to believe it, but you still can publish PRLs. So that's the success of the theory. It's not bad, because there is no fit parameter, and you look at, as Takashi says, you can predict other things. It seems to work quite well. So something perhaps is in there. The point is they put in a little bit of chemistry, local chemistry, and in the local chemistry there is a lot of truth, one has to say. Silvio.
You were starting to comment the line and then you were interrupted. Can you comment the line?
Sure, sorry. So the line is the prediction of this. Okay? So they predict that this structure is ideally rigid. It's not over-constrained, it's not under-constrained. On this line here, if you put in the right numbers, how the R depends on the concentration of the sulfur and the germanium, you get out this thing. And the observation is that the location, the concentration, composition where you have good glass-forming ability is where the system is neither over-constrained nor under-constrained. That is to say, it coincides more or less with the line. So if you have too much frustration, it's not forming a good glass. If you have not enough frustration or constraints, you're not getting a glass because it's not rigid. So that's basically the message. Okay. Well, not too much, because good glass forming ability means that you do not want to see the crystal, but if the system is too frustrated, it will do something that you do not like, perhaps phase separate or something like this. So you want to peak it a little bit, but not too much. Okay? That's the end of rigidity percolation. Chairman, whoever it is, make a call. 7 more slides. And Austin is, have you prepared your talk? No, you go on. Okay. I mean, huh? Yeah, okay. Bon. Mode coupling theory. So there will be 3 presentations by Bakshi, Miyazaki, and Bhattacharya on this, so I will be relatively short. What is the basic idea? So to start with, forget about glasses. That there is a technical machinery which is called the Moritz-Zwanzig projection operator formalism, which is useful if you have a system with many degrees of freedom, and some of them are fast and some of them are slow. And so this machinery is useful, or can be used, to obtain exact equations of motion for the slow degrees of freedom by technically eliminating the fast ones. Now, so that's a very general thing. For colloidal system, particle in a viscous system, this has been applied with a lot of success. It's a very good machinery. Now, you can apply this machinery to glasses by saying that you have the vibration physically, these are fast, and you have the alpha relaxation that is slow. And so the idea is now what you do is you apply the Moritz-Zwanzig formalism, and then since you end up with horribly complicated equations, you have to do some approximations, and this gives you the mode coupling equations. And just to give you a little bit of a flavor how this looks like, is that the degrees of freedom that they identify usually are the intermediate scattering function for a certain wave vector. And the Moritz-Zwanzig equation that are exact looks something like this. So the first approximation, this is a harmonic oscillator here, second derivative, and the restoring force with a certain frequency. And then you have this thing here, which is a damping. So it's a damped harmonic oscillator. All the horror is hidden in this function here. It depends on the wave vector and on time. And nobody can, I mean, formally you can write down what it is. In reality, you cannot evaluate. So what you do is to make an approximation, or quite strong one, which is quite uncontrolled, and you end up with something like this. And here what you have is, again, the correlation functions. So you see it's a differential equation in which this memory kernel here involves, again, the memory, time correlation function with certain factors here. Okay. Now, what are these factors? So this is, again, the equation. Now, I don't want to give the expression because the other speakers will probably do it. The only point is that this factor here, this kernel, depends only on static quantities. That is to say, on density, structure factor, 3-point correlative function, etc. On static quantities. That is to say, if you evaluate this and you replace the M by the MMC for mode coupling, so this is an approximation, then this tells you that if you know the static quantities, then you get the dynamics. Hand feeling is that if the static structure factor becomes more peaked, then this vertex increases, the feedback becomes, so the M increases, the feedback becomes stronger, and therefore the dynamics slows down with decreasing temperature. If this feedback mechanism is sufficiently strong, the system will completely arrest and you have the glass transition. So that's, in a nutshell, what mode coupling theory is about. And the other speaker will tell about the detail. In order to give you an idea of what's happening, this is hard-sphere system within this mode coupling approximation. And for different packing fractions, and you see qualitatively this does indeed look like the time correlation function that we look like. If you are inside this glass here, then nothing relaxes anymore. There is a critical temperature Tc, critical coupling, below which the system does not relax anymore. There you are in the glass state. And the alpha relaxation time is predicted to increase with a power law. Okay. What is interesting is that many years ago, Kirkpatrick, Firmala, and Wulenets, they looked at the mean field spin glass models So totally different from the structure class that we cared over. And so Dasgupta, Mizar, and Biroli will talk about these sort of models. And this here is, for example, a Potts class model, just to give you an idea. So you have spins plus and minus 1. And here you have random coupling. And so this is the energy function. What was interesting is that if you treat this model within mean field, and you look at the time correlation function, you find that you can derive exact equations for the motion for this time correlation, autocorrelation function, and they have the same mathematical structure as the mode coupling equation. So this was really surprising. Mode coupling was before of this result, was heavily attacked, and then these guys came up and said there is a model for which these mode coupling approximations seem to be correct. In the sense it's really exact. And the other thing that was the key message of these papers was that there is perhaps a stronger connection between the structural classes, that is, say, where you have atoms, etc., and these weird spin classes that were a totally separated community. And it's starting with this model that these communities started to talk to each other, and it was extremely fruitful. So very nice. So basically, okay. Last remark. Later on, Couliandolo and Kurchan generalized these equations of motion for the out of equilibrium situation. And so they got a theory for the aging dynamics within mean field in the glass phase. And Jorge Kurchan will talk about it, and Silvio, I don't know. Yes? Okay, a little bit. Good. So they will give you many more details on this aging dynamics of these sort of systems. Okay. Chairman, next step to possibility to step out. It's the last theory that I would present. 4 more slides.
We have some time for questions.
Fine. Okay. Okay. I give this last slide summary. So I did not tell you about all the theories, because too many. But so I took some of them that are not necessarily discussed here, which some of them are a little bit outmoded, but still in vogue. Main message of my talk, which I hope you got out something a little bit, is that the field is really complicated. There are many players, many theories, and many people that claim that's the ultimate theory. This is perfect, this is good. The reality is much sadder. None of the theory really works, but many of them are highly useful. But if you are a little bit critical, I'm not talking about fitting functions. I'm talking what I defined at the beginning as theories. Sometimes you have really fuzzy concepts. I mean, and you ask yourself, or you ask me, what this and that is regarding Adam Gibbs. And you're right. It's not clear what are these regions, etc. Do they really exist? And does it make, for example, the random first order transition? This was chopped off, but there you talk about interface tension. Does it make sense to talk about interface tension of an object that is 4 or 5 atoms across? Not clear at all. There are many problems in these theories. I mean, MCT, this approximation that I didn't show, but it exists, it's totally uncontrolled, not clear why on earth this should work. At the end, MCT works quite well, and you will see it in the other talks, but it's a surprise why it works. Adam Gibbs seems to work, it's not clear why it should work. So there are plenty of miracles that are happening that at the end the theories seem to predict something that is reasonable, but if you put this all together, you say that this is all contradiction. Nevertheless, the good message is that I mean, these theories, despite the fact they are perhaps wrong, or they are certainly wrong to some extent, but it seems that they have some grain of truth in it. And so they are extremely useful to advance the field, because they propose things to be tested in experiments or simulations, and that's what the theory is. They should propose you to think, to look for. And so all of the theories that I talked about, they made interesting predictions that challenged experimental data or helped you to rationalize certain experimental data. So it's good to have the theories around, but it's certainly still, it's an old field, but it's also a very young field because there's still a lot of things to do. Okay, so enough of rambling. Thank you very much for your attention.